Yes. At the flagpole. Sometimes people pray at the flagpole. Ms. Rice beats up her students who skip class. All right. In math class, we usually use the Cartesian. Has anyone heard that word before? Slash rectangular plane. We usually use the Cartesian or the rectangular plane. These points are in terms of x and y. Aha, it has a name. Cartesian, rectangular. Those are the things that we call it. Two different words for the same thing. Polar coordinates, that's what we're going to do for this unit. We're talking about polar equations, polar graphs, polar coordinates. They are used in navigation. So instead of finding your points by going left and right and up and down, it doesn't always make sense to use that type of notation. So polar coordinates are used in navigation, modeling gravitational fields, etc. I said etc. because there's more, but I don't know what it is. The polar axis is the positive x-axis. So right here, if this is what a polar grid looks like. So we're not talking left, right, up, down anymore. The polar axis is this one right here. And it's not the whole horizontal axis, it's specifically this part. So there's your polar axis. The center of the graph, this point right here, is called the pole. We've always called it the origin. Yeah.
You don't have to beat him up. He's scared.
Martin, I was going to tell your brother to let you know to meet me at the flagpole so I could beat you up at 3:57. Give me 2 minutes to get out there. Here's the notes. Yeah, so the pole is this middle point right here. There's a little arrow, but you can't really see it because there's too much going on in this. Okay. Polar points are written as, anyone have a guess as to what the 2 units of measurement are that we have for this?
X and Z.
What? X and Z. What do you think the 2, instead of left, right, up, down, what do you guys think the...
Something next theta.
There's going to be a theta. You guys see how the angles are? And then what else? Because I see concentric circles. What's happening with the circles?
Circumference.
Yeah, kind of circumference. They're like, this circle is how far from the center? 1. What about the next circle? What about the next one? How are you counting how far from the center they are? The radius. Yeah, so polar points are written as the radius and the angle, r theta. That's how we write polar coordinates. So if we were to draw a point is still going to be a little dot, right? There's our point. The way we're going to measure it is we're going to say this is theta. There's our angle, that's theta. And we're going to say that this part right here, however far it is from the center, that's the r. So that's how we figure out where our points are located. So this right here is your r length, and then this right here is your angle. Does it make sense how you'd use that in navigation? Like ships, at this angle, go this far from the center. When we graph things that are in the rectangular plane, we typically do right and left first and then up and down, right? If you have the point 3, -4, you go to the right 3, down 4. In polar coordinates, we go backwards. We locate the angle first. So if you're talking about a 60-degree angle, then you would locate this line right here is where 60 degrees is represented. And then from the center, if you wanted a radius of 3, you'd count out 1, 2, 3. So we graph the angle first, then we graph the radius. It goes backwards. The radius might be positive, which means you go toward the angle. Or the radius might be negative, which means you go away from that angle. So for instance, if we were to graph the point -2 pi halves, then the first thing I would do is locate where pi halves is, which is where? The top, right? It's the top. So pi halves is this line right here. but I'm going to do a radius of -2, so instead of taking from the center and counting out radius of 1, radius of 2 towards the angle, since my radius is negative, I would go away from it. So I'd count 1, 2, and then this point would be over here. A radius of 2, but you'd go down instead of up. And this brings up a special point, because if you look at this, I'm saying that this is the point -2 pi halves, but can you think of another way you could write that exact same point? Yeah, +2 3 pi halves. Because if you had located 3 pi halves first, and then counted from the center towards 3 pi halves, you could count 1, 2, it's in the exact same spot. So the special note here is that there are infinitely many ways to write every single coordinate. Infinitely many. So there's two ways you can get at more answers. You can have a positive radius and a negative radius. Since the positive radius goes towards the angle, the negative radius goes in the opposite direction of the angle. The other thing is you can write your angles, because you have pi halves is the same thing as 5 pi halves? Yeah, 5 pi halves. Yes. And then you have like pi fourths is the same thing as 9 pi fourths. Right? So if you add sets of 2 pi, you get to what is called a coterminal angle. It's an angle that has a different number, but it's in the exact same spot. So that's how you can have infinitely many ways to write each point, because you can add 200 or 2 pi, 2 pi, 2 pi, 2 pi to get different angles, and you can do the negative version of the radius and the positive version of the radius, and that's how we can get so many different answers for the same point. Does that make sense? How we can do that? All right. So for the first example, we want to find other points that are equivalent to 2 pi fourths. So first we're going to find a set of points that have a positive radius still. So if we're keeping this radius positive, then we want angles that are coterminal with pi fourths. We want them to be in the exact same spot as pi fourths. So what's another angle that's in the same spot? 9 pi fourths. What's another one? Yeah, -7 pi fourths. What's another one?
Isn't that 3 pi 7?
So you're adding a whole circle. How many radians are in a whole circle? 2. So I got 1/4. And then I can add 2. 9 pi fourths, add 2. 17 pi fourths, that's another one. Add 2. 25 pi fourths, that's another one. Or I can subtract 2, go the other direction. So there's our -7 pi fourths, -15 pi fourths would be another one, -23 pi fourths would be another one. So if we were to make ourselves a little shortcut for this, we would say that if the original problem is r theta, that's the original, then our other coordinates would be keep the r the same, and what are we doing to theta? We're adding 2 pi. So we're not typing the pi in the calculator, but technically we are adding it. So 2 pi, 2 pi, 2 pi. So I'm going to say theta plus or minus 2 pi k. What the k means is that we're doing multiples of 2 pi. It doesn't mean you only can add it once. It means you can add it repeatedly or subtract it repeatedly. So that's like the formula. If you're keeping the r the exact same sign, that's the formula for you being able to find other ones. Okay, so I'm going to go ahead to find the other ones. I'm going to go ahead and draw a sketch of this. So whereabouts is pi fourths? What quadrant?
First quadrant.
Yeah, first quadrant, halfway in the middle, right? Halfway in the middle. That was a little redundant. Okay, and then what was the radius? 2. So here's pi fourths right here. And then from the center we count out 1, 2. So there's the point right there. Okay. So if we have a radius of -2, then what angle would it had to have been for the negative to tell you to go in the opposite direction? 3/4 is over here. So 5/4 is over here. You see that? So if we said 5/4 is the angle we were starting at, and then we did a radius of -2, it would tell us to go the opposite direction. So it's almost like when we add pi, it's like the negative from the 2 and adding pi to our answer. 1π4 plus a whole pi is going to give you 5π4. It's almost like that's a double negative and they cancel out. Does that kind of make sense? Adding pi puts you on the wrong side of the circle. A negative radius cancels it out, puts you back on the right side of the circle. Does that make sense how we're thinking about it? Okay. So the -2 puts you on the wrong side of the circle, right? Mm-hmm. So does adding pi to π4. Adding pi to π4 puts you over here. So if we add pi to it, I'm on the wrong side of the circle, but now I've got a negative radius that's canceling it out and pushing me back on the right side of the circle. So it's kind of like two negatives canceling each other out. Yeah. So 5π4. So what I'm going to do over here is I'm going to say, if I take my r value and switch the sign of it, if it was negative to start with and I make it positive, or if it was positive to start with and I make it negative, whatever it is, if I switch the sign of it, then the first thing I have to do is take my theta and add pi to it. And that's because I have a negative for the r, that's putting it on the wrong side of the circle. And if I add pi to it, that also puts it on the wrong side of the circle, and those two things cancel each other out. And then put it on the right side of the circle. Does that make sense?
That makes sense.
Cancel, cancel, get you back where you started. Okay. All right. So now that I have a point to start with, what can I do to find other points? Yeah, add, subtract 2, right? So the other part I can say to this is, now that I'm on the wrong side of the circle and the wrong side of the circle and they cancel out, now to get more answers I can say plus or minus 2πk.
Okay, so we first have to find that.
So first, yep. So first you find the point that's like opposite, and then you can say, all right, now let's get some more. We get some more by finding coterminal angles, and that's the plus 2πk. Yeah. So now I can say, let me start with the 1/4 again. I had 1/4 to start with. Since I have the r is the opposite sign of what I started with, I'm going to add 1. That puts it on the wrong side of the circle. And now I can go ahead and add 2, get some more answers. So we're going to say -2 13π4, -2 21π4. And then I can also subtract 2, -3π4, -11π4. Okay. How are your brains with that? So if I was to plot all of these points at the same time, every single one of them would be right here. None of them would be in a different spot. They'd all be in that exact same spot. Yeah.
So why do we need to know other points that give you this like?
Because if they gave you a point like this, you would need to recognize that it really was the same point. It's kind of like if I give you 50 over 100, you have to recognize that's 1/2.
Okay.
You know what I'm saying? This is just like the polar version of simplifying fractions. It's just saying if I have 50 over 100 and I have 3 over 6 and I have 5 over 10 and I have 15 over 30, I recognize that all of those fractions are actually the same fraction.
Yeah.
I recognize that all of these points are actually the same point.
So it would be like if we're asked, like on a test, just any problem that involves floating points, we want to give them one.
Yeah, they might not ask you to give other points, but they might ask you to recognize which one of, like, they say match up the point, the graph of the point with this one, and you'd have to know that this is how you graph it, and that all of these could be the same. Or they could give you maybe a multiple choice question where they have A, B, C, D, E. Tell us which point is not the same as the other ones. You know what I'm saying? So you'd have to know, like, how they interact. Does that make sense?
Yeah.
So it's not like every time you write a polar point, I'm gonna say like write 17 other coordinates or the exact same. You know, like I'm not gonna do that. But it's good to at least know like yes, there's infinitely many ways you can write it, and I understand this pattern well enough that if I had to write some other ones, I could.
Okay.
Yeah. All right. So since we have the rectangular plane and now we have the polar plane, it's going to be good for us to convert back and forth between the two of them. And it actually comes, all the little formulas that we use to convert back and forth, they all come from what we've already learned about the unit circle. So if you guys remember how triangles from the unit circle are made, you typically have a point, right? There's some point on the edge of the unit circle. And from the center of the unit circle to the edge of the unit circle, we would call that a length of r. That's the radius. And then to actually find the x and the y coordinate of that point, we would go to the right a length of x and up a length of y, right? So we've got a right triangle built there. And then the measurement of the angle would go right here. So here's our theta. So polar graphs are in terms of r and theta. Rectangular graphs are in terms of x and y. So this is a situation that kind of gives us everything all at once. So converting to rectangular form, we're going to say that, sorry, I'm going to use what I know about triangles. I'm going to say that cos of the angle is what? X over r, so adjacent over hypotenuse, right? And if I wanted to solve for x, how could I do that? Multiply the r over to the other side. Okay. So x equals r times cos of theta. X equals r times cos theta. So if we are given the radius and we are given the angle, we can find the x coordinate of the point just by plugging those two things in. That's how we take the point, convert it to the x coordinate. What about sine theta? What would that give you? Y over r. So opposite over hypotenuse. So if we wanted the y coordinate, what would we do? R sine theta. Now, if you are making a cheat sheet for this unit, this needs to be on it. These are important. The other thing that would need to be on it would be these formulas right here. So those are the important formulas we've learned so far today. Okay, so now it says, for example, 2, to take that point that we were working with, 2 and then pi fourths, and to convert it to rectangular form. So we're going to say that x equals 2 cos of pi fourths, y equals 2 sine of pi fourths. And the only time we're allowed to use a calculator to simplify these is if the radian measurement that they give you is not on the unit circle. If it's not, then you can just plug it in your calculator. Pi fourths is on the unit circle. So that means we have to use the actual coordinates. Does anyone know? Yeah, so it's root 2 over 2 for the x coordinate, root 2 over 2 for the y coordinate. So then that means when we simplify this by hand, no calculator, we're going to say 2 multiplied by root 2 over 2, and 2 multiplied by root 2 over 2. And what do we get? Yeah, and it's the same for each of them. So the original point 2 pi fourths, if we write it in the rectangular form, is root 2 root 2. If you look at the little sketch that we drew, does this seem accurate? Yeah, if you compare it up here, did it go to the right and up the exact same amount? Yeah, it looks like it. Okay. All right, next page. All right, converting to polar, we're going to draw the same picture. So we still have some point on the edge of the unit circle. We still say from the center of the graph to the edge of the unit circle is the radius of the unit circle. We still say that to get this point right here, we go to the right x and up y. And we still say that that right there is the angle theta. And this time, to get our equations, we're going to use the Pythagorean theorem. What does the Pythagorean theorem say?
A squared plus b squared equals c squared.
So in terms of this triangle,
X squared plus y squared equals r squared.
now for us to get this so that we can isolate the r, because we want to be able to take an x coordinate and a y coordinate and get an r coordinate from that, how could we solve for r? Square root each side. So we're going to say r equals the square root of x squared plus y squared. Alright. Now, we use sine theta, we use cos theta. Which one did we not use? So tan theta equals y over x. And if we had an x coordinate and a y coordinate and we wanted to get the coordinate for theta, then how would we solve for theta? Yep, so theta equals tan inverse of y divided by x. So those are the other two formulas that we would want on a cheat sheet. I'm going to be honest, I don't really memorize these. I just kind of know where they come from. So once I'm doing this unit a lot, then I kind of have them memorized for that unit, but from year to year, I always just go back to that picture. So if you brain fart on a test, you can always go back to where they come from to find them.
Won't get to that.
Your brain wouldn't get there? Are you sure? Pythagorean theorem? SOHCAHTOA? That's all I did.
I'm on very close.
Yeah, SOHCAHTOA.
I did SOHCAHTOA, Pythagorean theorem.
This is not for the
Alright, so now it says to convert the point 2, -2 to polar form. So for the r, what? Ooh, that's a bad looking r. For the r, for the r, what do we do?
Here, right.
2 squared plus -2 squared is 8. Square root 8, okay. And theta is tan inverse of -2 divided by 2. That's tan inverse of -1. And this is where we have to think, is this on the unit circle? If it's not, I can type it in my calculator. If it is on the unit circle, I need to not use a calculator and just think about it. So when you have tan inverse y divided by x, you have to think on the unit circle, what are the fractions, the root 2 over 2, the root 3 over 2, the 1 over 2? Is there any way for the y coordinate and the x coordinate to be divided to make a -1?
Yes.
Yes. Where does that happen? It happens in 2 quadrants, right? It happens in the second quadrant. That's where x and y are opposite signs. It happens in the fourth quadrant. That's the other place x and y are opposite signs. Second quadrant and fourth quadrant. Where is this point located? You go right 2 down 2. Fourth quadrant. Okay, so what's the angle in the fourth quadrant where the x and the y divide to make a -1? 7 pi fourths. So we're going to say that theta is 7 pi fourths. So the other place where tan inverse is -1 would be 3 pi fourths. And we know that that is the wrong answer because it's in the second quadrant, and this point is in the fourth quadrant.
So how did you do that again? I was just confused over the tan inverse. Did you do anything with the tan inverse, or did you just find
The tan inverse tells you your answer should be an angle. Because tan of an angle gives you a fraction, a ratio of opposite over adjacent. Tan inverse of a fraction gives you an angle as an answer. So when we were doing tan inverse, we knew that our answer should be an angle. Alright, so if we look at this, we're going to go ahead and write this like a point. We got r, and we got theta. And if you were to graph the point right 2 down 2, does that seem to fit if we were to do 7 pi fourths and then go out a radius of root 8? Seem kind of reasonable? Yeah? Alright, so that's all the stuff with points. That's how we graph points. That's how we find equivalent points. That's how we convert our points back and forth. How do we feel about polar points? Rectangular points, converting. Do we feel kind of okay on those? Okay. All right, next we're going to look at equations. Woo. When you are converting between rectangular and polar equations, the goal is to make substitutions. And the substitutions are based off of those 4 equations we already wrote. The r, or x equals r cos theta, y equals r sine theta, r equals the square root of x squared plus y squared, theta equals tan inverse of y divided by x. So those substitutions are still the same 4 equations we already worked with. So first make substitutions, then simplify. And you keep simplifying until you have a recognizable equation. So how do you know when to stop? You stop when you know what the equation is supposed to look like. So does the equation give you a line? Does it give you a circle? Does it give you a parabola? You keep going until you get a recognizable equation. So in my opinion, it's a little bit easier to convert from polar to rectangular because we've been doing rectangular equations for a long time. So when you convert it to rectangular, you're like, oh, that's y equals mx plus b. I'm done. Or, oh, that's x squared plus 2x equals y. That's a parabola. I'm done. I can recognize it. When you convert from rectangular to polar, it's a little bit harder because this is the first time we've dealt with polar, so we don't necessarily know what recognizable equations are. Does that make sense? Since that's how you know where to stop. So what I did is I made you guys a list of what recognizable polar equations might look like. So this first set, these are straight lines. These are different ways that straight lines might look in polar form. Anyone know how we would graph theta equals pi 6?
Pi 6.
Yeah, just pi 6. Just find a line pi 6, which is just like up a little bit, right? So anytime you have a theta equals equation, this is a line that goes through the origin. That's a line that goes through the origin. R equals 5 cos theta. If you were to multiply the cos to the other side, what would you have? Yeah, you would have 5 equals r cos theta. And what is r cos theta? X. So then you have x equals 5. What's the equation of x equals 5 look like? It's a straight line. It's vertical, right? It's a vertical line. So anytime you have something, it could be 5 over cos theta. It could be 5 over sine theta. What would 5 over sine theta be? Yeah, y equals 5, that'd be a horizontal line. Okay, so it could be 5 over cos theta, 5 over sine theta, or instead of writing 5 over cos theta, they could just write 5 secant theta. That would still be a vertical line because you're just using the alternate trig function. Okay, so these are horizontal and vertical lines. And then this last one is still straight lines. It doesn't go through the origin. It's not perfectly vertical or perfectly horizontal. It would have some other y-intercept and x-intercept. Right? So these are just regular lines. Okay. The next one, these are all, actually you might be able to tell from the first one. What do you guys think that graph would look like? It's a circle. You guys see how r equals 4 would be a circle? Yeah, it's just like find the line that represents a radius of 4 and then follow it all the way around. That's a circle with a radius of 4. So these are all circles. So this first one is saying go out 1, 2, 3, 4 and draw that circle. That's what the first one is saying. So this first one, the circle is centered at 0, 0. These other ones, the center has shifted, but they're all circles. All 3 of those are circles. So this one would be one where the center has shifted left or right or up or down. Do you have a guess? Up or down. Why? Why do you know it's up down? Because it's sine, and sine corresponds with y. That makes sense? Okay, so this one's been shifted up or down. What about this center? Shifted up, down, and left, right. Okay. Right, so there's circles. These next ones are conics. What do I mean by conics?
Hyperbola.
Hyperbola. What's another type of conic?
Hyperbolas.
Parabolas. There's one more that starts with an E. Ellipse. Circles are technically conics as well, but we typically see them from this. Okay, now if you were in pre-calc, we would hit this real hard so you'd actually know what you'd be able to look at the equation and know which one it is, but it seems in calculus you don't need to get that in depth with them. So we're not going to go too far into those. However, it would still be good for you to be able to recognize, oh, that's a conic. Okay. All right, and then the last one, I call them special polar graphs. These are ones that in rectangular form don't have a name. Like we do not graph these in rectangular, we only graph these in polar. Okay? So they're not going to be ones we've seen before. The first one is a cardioid. What does cardioid remind you of?
A heart.
A heart. It's a little heart shape. And I use the term heart loosely. It is loosely heart shaped. It's a little bit heart shaped. Did you guys do these last year? No?
Nope.
Yes.
Yeah, I mean, but I never got a name for it.
Yeah.
No.
They look like this. So like loosely heart shaped. They're mostly called hearts because they have that like dimple where it inverts. That's why. The next one, if you're being fancy when you say it, there's like I say limacon because I like to just pronounce things phonetically. I think it's technically limason, and there's an accent with the C, but I don't know how to draw it. So we can say limacon in this room and not judge each other, but maybe don't say limacon outside of this room because people might think you're weird. Yeah. So now these, I put sine for all of them, but it could have been cosine. So this one, my picture goes up and down because it's a sine graph. What would happen if it was a cosine graph? It goes side to side. If you notice in these two, this number right here and this number right here are the exact same size. That will always be the case with a cardioid. They will be the exact same size. A limason, whatever, it's got the same shape, but it doesn't dimple. It just is a little curve on the inside.
A lima bean.
Yeah, it looks like a lima bean. Yes.
Lima beans.
And you'll notice on this one, the first number is bigger than the second number. That will always be the case. Now, these pictures go up because there's a plus there. If there was a minus, they would have gone the opposite direction. So since it's sine, the picture's still up and down. It goes up because it was a plus. If it was a minus, it'd go the other direction. Okay. This one is a limacon, or a limason, whatever you want to say, with an inner loop. So it looks like this, but it loops in the center. There's a little loop. You will notice how terrible my drawings are once you actually see these on your graphing calculator. You'll be like, wow, she really butchered that. All right. This one, these are roses. These are the ones that are going to be fun. They do not look like roses at all. A daisy would be a more accurate name for them. I don't know why they call it a rose, but it's so they have petals. So this one, I said 4 theta, so this one would actually have 8 petals, because if it's an even number, you double it. So if it said 4 theta, you'd have 8 petals. If it said 12 theta, you'd have 24 petals. If it's odd, it has the exact same number of petals. So if it's 5 theta, it's got 5 petals. And the reason is it doesn't actually only have 5 loops, it's just that the loops go on top of each other. So 5 theta still has 10 loops, it's just that the loops are redundant. You draw 5 loops and then the next 5 loops go on top of it. All right. So a rose, so this one would have 8 petals, so it'd be like,
Yeah.
it'd be like
Is
that.
that what it really looks like?
Yeah, I'll show you.
I graphed the first race.
Yeah, actually, let's go ahead and, do you guys have your calculators on? So first you have to switch to polar, so you have to hit the mode button and go down to polar.
I'm getting
Yes, so we have to, we're going to go ahead and graph this. So we can go ahead and do the first one, 3 plus 3 sine theta. Now, I still like you guys, but one of you guys stole one of my calculators. And I know it was you, because I had counted them after second period, and they were all there. It happened before spring break. So, I'm just letting you know. Maybe check your backs.
You see what my name?
I don't think you did it on purpose, but one of you definitely stole my calculator. Alright, so go ahead and hit the window button. Your theta min should be 0. Your theta max should be 2 pi, and when you type in 2 pi, it's automatically going to put the decimals in like that. For your graph to be the most accurate, you want your step to be like pi 12ths. Pi 6 might be okay. If you guys remember when we were doing the parametric graphs, if your t step was too small, because it makes like little straight lines. The smaller your lines are, the more curved they are. If you make your lines too long, then your graph looks a little bit like pixelated, kind of. So it's like, So I think I did pi 12ths. Anyone else do pi 12ths? Okay.
So I do like pi 200.
If you do pi 200ths, you're going to be waiting forever while it graphs.
Yeah, so somebody just do it right now. Don't use their calculator for the rest.
Yeah, so I don't know if I do that. All right, and then the x min and the x max is how far left and right. We want our graph to go how far up and down, and I'm not going to adjust that from the typical graph just yet. I just want to see what it looks like. So if you hit the graph, there's our cardioid. Oh, I drew it backwards. But it dimples in the middle. If you want to be able to see the dimple better, I can take out the y min numbers, make those quite a bit smaller. And then this maybe. Then you can see the dimple better. So the cardioids, they dimple in and they touch the pole. They always touch 0. They don't go through it, they just touch it. They hit 0, bounce off of it. I also think they kind of look like a bug.
And that's all I got.
All right. Let's go ahead and do the next one, 3 plus 2. So, if you can see here, that dimple smoothed out. You guys see it? It smoothed out. This one, it looked real flat. You're going to be able to see the dimple better if your numbers are further apart. So I'm going to go ahead and change it to 5. I'm going to make my window a little bit bigger again. Once I make those numbers further up, you still can't. Maybe. All right. And then if I do the next one, you can see it makes that loop. If I make the numbers closer together, you can see how that loop gets, not only does the overall shape get smaller, but that loop got smaller. Can you guys see that? All right, the next one, let's go ahead and do the rows. So 3 sine of 4 theta. Ta-da!
I have a question.
Yeah.
So if I were to make, hypothetically, if I were to make 4 1,000.
That would take your calculator a long time. They would have 2,000 petals. It would just take a long time.
But would they still, they would all reach the middle, right?
Yeah. Now this, if I want my petals to be longer, what do you think I do if I want them to be longer?
Change the 3.
Yeah, change the 3. So if I make it like 6, now my petals are bigger.
I think your calculator is broken.
Oh, because your theta step is bigger.
Just stop trying.
That's like when
You know, you should have
we had to do a project
Or just
with
get
how
you
we
wanna
were
type in
running
your
on this graphing website. We had to make a picture with all these different
Yeah.
I wanted to see what it was.
All right. The last one. So this here, your n, this number in front of theta, it can be all sorts of different numbers. It doesn't have to be a 4. It could be a 3. N is typically greater than or equal to 2. Typically. Okay. The last one, if you guys notice, this is the only one that says r squared. So you're either going to see it written like this, or you might see r equals the square root of 4 sine 2 theta. You would see either one of those. And these are lemniscates. I have no idea if I'm pronouncing that correctly.
It's lemniscates.
Lemniscates. I like that better. Let's use that. So if I do square root of 4 sine 2 theta. Oh. That's right, folks. It's the little infinity sign.
Nice.
It's not good 500 credits.
Yes. It just gets real dark. Your calculator doesn't like that one.
Yeah, it literally looks like a dark blob.
Yeah. Too many petals and you got a blob.
Let's see if we can make them.
It's more fun if you do like 25. well, I guess double that.
I
30
made
or
them
something.
longer.
So you just made a circle bigger.
Yeah.
Let's see how big we can make them.
Yeah. All right.
Oh, shit.
So these are the special names. Now, this stuff, are you listening? You do have to memorize the difference between these. Because as we move forward into like, technically all that we've done right now is we've reviewed pre-calc concepts. When we get to the calculus concepts, they're going to say like, hey, find the surface area of that, right? Find the arc length of that. Find the area of that. We're going to be using derivatives and integrals. If they want you to find the size of the inner loop of something, you kind of have to know like which equation you're dealing with. Does that make sense? So you are going to need to memorize cardioid is the one that has two numbers that are exactly the same. The limacon where it just divots in, that's going to be the one where this number is bigger than that number. You're going to have to memorize that the sine graphs are the ones that go up and down. Those are their axis of symmetry is the vertical axis. That makes sense? Axis of symmetry is the vertical axis. That if I were to put a cosine there, that the axis of symmetry would be the polar axis for the horizontal axis. You're going to have to know if it's a rose, how many petals does it have? So let's say they want you to find the area of one petal of the rose. So you might do the math to find all 8 petals and then divide your answer by 8 to find the one petal. So you don't have to necessarily be able to sketch every single one of these by hand, but you do have to understand the numbers well enough to know, okay, this is what they're saying, this is what I actually need to do. Does that make sense? Okay. And we want to understand them well enough that we're not overly dependent on our calculator. So when we look at these today, I'm going to ask you to graph a lot of them on your calculator so you can start to see the patterns and get like an intuition for it. But these questions could be fair game on the calculator inactive portion of the AP exam because maybe the math that you actually do is easy math to do by hand. Does that make sense? So you have to have some level of understanding of these just in case they're not on the calculator section. Okay, so we're going to go ahead. If you look, I gave you a little like, oh my gosh, I forgot the notes were still going. These are some more conversions.
42.
Yeah, these are some more conversions. We're just converting equations instead of points, but we still use the same little formulas. So we had x equals r cos theta. Y equals r equals and theta equals all right. So if I have r equals 2 and I want to convert that into rectangular form, what could I do? I don't want to have any r or theta in the problem. I only want to have x's and y's.
2 equals.
So take the r out and replace it with so this r equals, sorry. So I'm going to take this r out and I'm going to replace it with square root x squared plus y. I was like, these are the
I thought you were taking
formulas.
the other.
Yeah, I got you. All right. Now our goal, remember, we just made the substitution. Now we're going to be simplifying until we get a recognizable equation. That's the goal. So what could we simplify to get closer to a recognizable equation? Square it, square both sides. So we have x squared plus y squared equals 4. Is that a recognizable equation?
Yes.
Yes. That's a circle centered at 0 with a radius of 2. That is a recognizable equation right there. So we are done.
Somebody just let the sandwich crust.
I mean, yeah. All right. So the next one, theta equals pi thirds. We have theta as tan inverse of y divided by x. So I'm going to go ahead and write tan inverse of y divided by x equals pi thirds. And for this to become a recognizable equation, I probably don't want a tan inverse there, right? Rectangular equations in terms of x and y typically don't have tan inverses in them. Like sometimes, but usually not the way it's written. So, tan each side.
Or you got some rays or something? Or just like a container, just put it in.
So y divided by x equals tan of pi thirds. I'm going to picture my unit circle here. Pi thirds is right there-ish. Anyone know the x and the y coordinate right here? 1/2. And then root 3 over 2. Okay. So, and I know it was 1/2 root 3 over 2 because it goes over a little bit and up more. So tan is y divided by x. So it's root 3. So I'm going to say y divided by x equals root 3. So I've made all my substitutions. Now I'm just simplifying until I get a recognizable equation. Do rectangular equations typically have y divided by x in them? No. So what should I do? Multiply x to the other side. So I'm going to say y equals root 3x. What type of equation is that? Linear. That's a straight line. It goes through 0, and it has an ugly slope of root 3. That's the slope. So that's ugly, but that's what it is. You do not have to put the plus 0 on the end if you don't want to. But that's a recognizable equation because it's in y equals mx plus b. All right, r equals secant theta. Does that match any of these? Is that helpful for us? No. So how could I rewrite secant theta? 1 over cos. So r equals 1 over cos theta. Okay. So that's beneficial, but we're not quite there yet. We still need to see one of these things. So now what could we do? We don't have anything for cos all by itself, but we do have something when the r and the cos are multiplied together. We could move the cos to the other side. So if you multiply the cos over, you get r cos theta equals 1. So x equals 1. What kind of equation is that? It's a straight line. That's a vertical line. So that's a recognizable equation. That means we're done. All right. Now, we've got a plain old r. That's good, right? Because we know what plain old r is. But we've got a cos theta. And up here, we don't know what cos theta is. We just know what r cos theta is. Can you guys see that? So what we're going to do on this last one is we're going to take the entire equation. We're going to multiply the entire equation by r. You can do that as long as you do it to the whole thing. So that gives me r squared equals 3r cos theta. All right. So r squared, what's r again? Okay, so we've got r squared, right? So the inside is the r, and I'm squaring it, equals 3x. So when we're taking it from polar equation to rectangular, we want to get rid of all the r's and all the thetas, and we only want our answer to have x's and y's in it. We don't want it to be half and half. We want it to be all x's and y's. All right, what happens to this side when I have the square root and the squared? Cancel. So I've got x squared plus y squared equals 3x. Do we know what this is? It's a circle? That is not, it's not an ellipse. Do you know why it's not an ellipse? The coefficients to the x squared and the y squared are the same size. That means our radius up and down and our radius left and right are going to be the same. There's a 3x, that's going to change the center, but it's not going to change the radius. So this is a circle. I'm going to go ahead and take this circle and write it in the general conic form. So I'm just going to move that 3x over and make it equal 0. But this is a recognizable rectangular equation. We've seen equations that look like that before, so I think we're done. Okay. Do you guys see how, do you guys think that if you were to do these equations, you would know when you were done? Kind of recognize when you're done?
Yeah, but I don't know if I didn't
Not
get
that
there.
one.
If I could get to that point, yeah.
Yeah,
If you get to that point, you
But
know
I
you're
can't, I don't think I can
Okay.
start off.
Now, in pre-calc, we give you tons and tons and tons of these, and you should be able to do really complicated ones. In calculus, I don't think that you doing complicated ones is as important, because we're just looking for you to be able to get there and then do other things with it, as opposed to this being the end all of what we're doing. Okay, so I don't think you're going to have to do any that are super crazy. Okay, converting from rectangular to polar form, your recognizable equations are going to be these ones. Okay, so what do you guys notice about these equations? It's r equals something, right? What are the two exceptions to that? Theta equals, so that's a straight line that goes through the center. That's one exception. What's the other exception? R squared. Okay, but the rest of the time you're always getting r alone. And even in this one you can technically get the r alone. Okay, so let's go back. We know that our goal now is to get it into polar form. We have to get rid of all of the x's and y's and only have r's and thetas. And we know that most of the time the r should be completely by itself on the left side.
So you square root
So I'm going to square root each side. Why am I doing that?
to get the R.
Yeah, so square root of x squared plus y squared is just r.
R equals 4.
R equals 4.
Oh,
Good.
that's not
It's a recognizable equation because the r is isolated, and I recognize it from the previous page. What is this? It's a circle. Recognizable equation. Okay, how about this one?
Theta equals
And then what should we do? Divide by sine theta. So we can say r equals 8 sine over sine theta. I know that I'm good because the r is alone, and I recognize this from the previous page. The previous page had problems that were kind of like this. What's an alternate way to write this exact same answer? R equals 8 cosecant theta. The same answer, I'll take both. I'm good with either one of those. What type of graph is this? Straight line. Straight line. All right. When you do the special polar graphs, here's some things that I'm going to want to know. I want you to be able to look at the equation and tell the name of it, or look at a picture of the graph and tell the name of it. I want you to be able to look at the equation of a rose and know the number of petals that it has. Does it have 8 petals? Does it have 3 petals? I want you to be able to know the interval to trace the entire curve once. So the way you can find that out is by looking at your window. So my window from here goes from 0 to 2 pi, and I was able to see the whole picture. If I go from 0 to 1 pi, can I still see the whole picture? No. So when you look at these, your answer is pretty much always either 2 pi or 1 pi. And that's how you can figure it out, is we're just going to practice these a few times just looking at them. You're going to graph them on your calculator and get an idea of which one needs which interval. They're very consistent. So it might be like all of this whole family of graphs, they always do 2 pi. I just always know the interval is 2 pi. This other family of graphs, they always just need pi for me to see the whole thing. Okay, does that make sense? Okay.
I got a question.
Yes.
So what about the roses with the odd number? They go over twice. Do I need? Because I only see it once.
I believe we still call it 2 pi because even though the petals are redundant, those points still count. Yeah. Yeah.
So if we got asked about the number of petals, would we say 3 or would we say 6?
Typically they would say 3. Yeah.